at section 1.5. 1.5 is talking about collecting different kind of sample data. So previewing what the key concepts are in this one. If sample data are not collected in an appropriate way, the data may be so completely useless that no amount of statistical torturing can salvage them. If you don't get good data to start with, there's nothing you can do to be able to make sense out of what you have. If you were to do a convenience, or well, not even convenience, if you did the survey where everybody decided whether they responded or not, and it was only people that were really mad that responded, well, then it's going to sound like that group is horrible when it's just the rest of the people didn't respond to it. Or like I said, if we were trying to look at the percent of male-female ratio here on campus and we went to the girls' dorm to do it. It doesn't, the way that we collected our data, horrible collection method, that we've already distorted the data so bad that it doesn't matter what we do to it, you can't make any sense out of it. So the method used to collect the sample data influences the quality of that statistical analysis. Of particular importance is the simple random sample. You will hear the words simple random sample, I don't know how many times this semester, because having a good simple random sample is an important first step, and it's an assumption that is made before we do majority of the rest of the statistics we use for the sample data. And so making sure that we've got a good sound sample first is extremely important. So going through and just sort of looking at what does that mean is where we're going in this chapter, in this section. First of all, we have the observational study. That is when you're observing and measuring specific characteristics without attempting to modify the subjects being studied. That prospective survey that we looked at last time, which was talking about following the nurses and just having them report on different health issues, that was an observational study. They were not bringing the nurses in and giving them all kinds of extra material or helping them with their diets or influencing, giving them this new medication to try to affect their health. All they were doing was every year asking them to report in on this survey what they're observing. And so it was just an observational study. A lot of what we look at is your observational studies. There's a lot of times that's the type of stuff that's being pulled out of it. But we also have the option of an experiment. An experiment is when you apply some treatment and then observe its effects on the subjects. So if we were trying, my in-laws are on this new weight loss program through KU Medical Center. And so they are in an experiment where they are applying this different type of diet where they've got boxed meals that they're supposed to eat and record all of their food and all this kind of stuff. So it's already pre-planned for them what they're going to have. They're applying a treatment to them, and they're observing what happens. How much weight do they lose? How many inches do they lose as they're using this new weight loss technique? And so that would be an experiment. They are applying something to that group, and they're going to compare it to a control group of people that are not using this different weight, this new diet plan. How much weight would a normal person lose during that time period compared to how much weight people are using with this new treatment that they're doing? So that's an experiment. And how we can make conclusions about things, it's a big difference between if it's an observational study or if it's an experiment. When it's an experiment, you can do cause and effect relationships. We can actually come to the conclusion of saying by being on this new program and only eating these boxed meals with some fruits and vegetables has caused them to lose weight. On the other hand, if we're just doing an observational study and we're just observing what they're doing, even if those people were on this new box thing and not necessarily on an experimental treatment plan that they're comparing it to a control, you might not be able to say it's a cause and effect. You might just be able to say there's this correlation between the two. Because it could be that the people they picked to put in this new study have some other issue that they're doing that's causing them to actually lose the weight, and it's just by happenstance that they're losing the weight during that time. So trying to make sure that they are observing other outside influences to make sure those aren't also impacting things is part of that difference. So that's one of the things we'll talk about. I think that's like chapter 9 is when we get to work with those. No, that's not right. Chapter 7. Chapter 7 is where we'll be looking at those again. But having that difference of whether it's an observation or an experiment makes a difference on what we can do with this information. So our simple random sample. You select N subjects in such a way that every possible sample of the same size N has the same chance of being chosen. So, if I was looking for a simple random sample of college students, let's say I wanted my sample to have 20 students, I would need to make the decision on how I picked my 20 students in such a way that every group of 20 students has the same chance of being selected. That there's not something that's influencing that, this group might get picked, but this other group, they don't stand a chance on getting picked. That every group, it is not every individual has the same chance. It's every group of that same size of 20 has an equal chance of being selected. Questions yet? A random sample is a little different than a simple random sample. A random sample is when members from the population are selected in such a way that each individual member in the population has an equal chance of being selected. So this is just looking at each individual alone and not necessarily that group of whatever the size is, group of 20 for instance. That this, if you're doing just a random sample, then each student has an equal chance of being picked in this sample. Notice the samples do not have to be of the same size, and the focus is that each individual is equally likely to be selected. So if you're talking about a random sample, it might be that the way I design my sample, that sometimes I might, the way I pick it, I might pick 25 students, and the next time it might have been 32 students. So the sample size does not stay consistent as you're doing the random sample. Also, each individual has the same chance of being picked, but again, it's not that same size group having the same chances for the entire group to be picked. And we'll look at some more examples of what is and is not as we go, but I wanted to go through the definitions first. Now, a probability sample is selecting members from a population in such a way that each member of the population has a known, but not necessarily the same chance of being selected. So if I was picking students, then if I was picking NCMC students, and the way I picked my sample was I was just going to pick 2 classes. Out of all the classes NCMC offers, I'm going to pick 2 classes. I'm just going to take everybody from that group. Well, the probability could be calculated for each person. And yeah, let's make it easier. Let's just do 1 class. We can calculate the probability that your class, that one class is being selected. That probability is not going to be the same for every student because some people are in 5 classes, some people are in 4 classes, some people are in 2 classes. So the probability for each person is not staying consistent throughout things. But if I just went with, I'm going to pick a class and I'm going to come and observe or take information from each individual that's in that class, that would be a probability sample. So you're keeping, the probability is a number that we can calculate for each person, but it's not staying consistent throughout things. Questions there? Again, the focus is on the individual's chance of selection, but some may be more likely to be selected than others because those people that are in 5 classes have a better chance of getting picked than those people that are only in 1 class. So looking at some examples and trying to decide if these are random samples or simple random samples. All of these are probability samples. We can calculate out the probability for each individual. But I want to know if this one's going to be a random sample or a simple random sample. So this is number 21 on page 36. Pharmacists typically fill prescriptions by scooping a sample of pills from a larger batch that is in stock. A pharmacist thoroughly mixes a large batch of Lipitor pills, then selects 30 of them. Does this sampling plan result in a random sample? So does the probability that each pill gets selected have the same probability? Thumbs up if you think it's random, thumbs down if you think it's not a random sample. Okay. All 30 pills that we're going to pick, or each pill that's in there has the same probability. It's 30 out of however many pills are in there. Because he shook it up, there's nothing that says, just the same, first ones coming out have to be picked type thing. So each one of them has a equal probability. Since it's a random sample, we have a possibility that it's a simple random sample. So now the question is, does every group of 30 have the same chance of being selected? Thumbs up if you think any group of 30 could be picked. Thumbs down if you think it's not a simple random sample. Okay, is there anything that says that there's some pills that cannot be picked? Once I start picking, it's not saying that once I start picking these first two that now I'm throwing out, these others can't be selected. Each group of 30 has the same chance. Again, he shook this up. It didn't just have this one selection that we had to pick. By shaking it up, he's made it to where this is a good, simple, random sample. Any group of 30 out of that pill bottle has the same probability of being picked. So this is a good example of a simple random sample. Okay, same thing on this one. This is number 22. A quality control engineer selects every 10,000th M&M plain candy that is produced. Is this a random sample, and is this a simple random sample? Okay, first of all, is this a random sample? Thumbs up if you think this is a random sample. Thumbs down if you think it's not a random sample. Does every M&M have equal chance of being selected? Why? Okay, so if it's every 10,000th, who's doesn't have the same chances? Okay, once you pick the 10,000th one, 10,001 does not have any chance of being picked in my sample. So we do not have each one of them having the same probability of being picked. If random samples thumbs down, we don't even have to think about simple random sample. There's no chance. So this is a case where it is not either random or simple random. Now, we're going to talk about different types of samples in just a second and procedures for calculating it, which unfortunately this is one that's used frequently, but it's not a good simple random sample. Okay, number 23. ABC News conducts an election day poll by randomly selecting voting precincts in New York, then interviewing all voters as they leave these precincts. Does this sampling plan result in a random sample? Does every individual have equal probability of being selected? Okay, thumbs up, thumbs down. Is this random? Does every individual have the same chance of being picked? If we have, I don't know how many voting precincts are in New York. Let's go with 30. If there's 30 precincts in New York, and they randomly pick a precinct and interview every single person that leaves that, does everybody have the same chance of being picked? Yeah, everybody has a 1 in 30 chance of being picked, because if your precinct's the one that's lucky, you get to talk to them. If yours is one of them that's not, then you don't. So this is a random sample. Is it simple random? Does every group of 100 voters have an equal chance of being picked? How can it not happen? What's a group that couldn't happen? We're just in only New York, so we're not worrying about Missouri people in this one. How can I not get a sample of 100 people that's using this method? Okay, well, actually, one problem is every single polling district does not have the same number. And so by picking one of those polls, I've already made it not simple random because they're not staying the same size from one to the other. But if you're just even talking about groups of something, is there any chance that by doing this method I can get somebody from all 30 precincts? I don't have a chance of that. So by having people from different precincts, this method doesn't get it. So each group of whatever size we're picking does not have the same chance because it can't cross over these the different precincts. Once you're in a precinct, that's how you're picked whether you're in it or not. So it's not each group of the same size has the same chance of being picked. Okay, number 24. In order to test for a gender gap in the way that citizens view the current president, the Tompkins Company polls exactly 500 men and 500 women randomly selected from adults in the United States. Assume, and this is a big assumption here, assume that the numbers of adult men and women are the same. So with that, is this a random sample? Does every individual have the same probability of being selected? Thumbs up, down. Okay, each person has the same chance, however many people there are, or however many, 500 men out of however many men there are, 500 women out of, and we're saying it's the same number of women. So it became a random sample. Is it simple random? Does every group of 1,000 have the same chance of being selected? Why down? What's not simple random? What's not simple about this? What? Okay, there has to be 500 men, there has to be 500 women, so what group of 1,000 can't happen? Can I have a group of 1,000 women? If it was a simple random sample, that is a possibility. There's no way to have those uneven numbers with this one, that every group of 1,000 does not have equal chances of being selected. Now, depending on their method and assuming that the method they're getting their 500, it could be a simple random sample of the 500 men and a simple random sample of the women, but when you put the two pieces together, it's no longer simple random because you've fixed how many men and how many women can be in there. And so you can't get groups that have those uneven quantities. So that one's not simple and a simple random sample. Okay, number 25. NBC News polled reactions to the last presidential election by surveying adults who were approached by a reporter at a location in New York City. Is this random? Does every individual have equal chances of being selected? Thumbs up or down. Does each individual have the same chance of being picked? How could that not happen? How can we not have the same probability of being picked by this reporter who's standing on a corner? If I'm not in that section of town, we're talking New York. New York's enormous. If you're looking at being in downtown Manhattan and you don't work downtown Manhattan, you don't go there unless there's some sort of important thing going on. So the chances of the reporter being there, whether it's really busy and lots of people go by, but if you stay away from that area of town, you don't stand a chance of being selected. So by doing this one's considered a convenient sample. It's not a random sample, so it's very definitely not a simple random sample. Okay, if we look at number 26. A classroom consists of 36 students sitting in 6 different rows with 6 students in each row. The instructor rolls a die to determine a row, then rolls the die again to select a particular student in the row. This process is repeated until a sample of 6 students is obtained. Thumbs up or down on random. Does every student have the same chance of being picked? Okay, random. Each student has the same chance. Is it simple random? Does every group of 6 have the same chance of being picked? Yeah. That once you've picked somebody, it doesn't eliminate everybody else in your row or anything like this. That once you picked one person, it's starting all over again. And if they just happen to keep rolling the same numbers, they would, and picking the same student 6 times, they'll keep moving on until they get 6 different students. So each group of 6 students stands the same chance of being picked. That it could be that everybody in the first row gets picked. It might be one person from each row. There's no set way of how we're going to determine which group of 6 there is. That once somebody's selected, it doesn't change everybody else's chances. All right, so each of these different ones we were looking at are examples of different kinds of sampling techniques. The systematic sampling technique. You select some starting point, and then you select every kth element in that population. So for this one, we're saying we're going to start with the third man, and then we're going to go with every third man is going to be picked. The systematic approach was the same as our M&Ms. That you picked every 10,000th M&M was going to be selected to be tested. Well, if by chance, if you are the control person at the M&M factory, and you always go with every 10,000th M&M gets spit out, well, if for some reason your machine has issues during that first 10,000, you're never going to notice it. Because you don't start doing your sampling techniques until the 10,000th, and then you've got another 10,000 before it's checked again. And so by doing that technique, you're not getting a good, simple, random selection as you're doing things. Convenience sampling uses the results that are just easy to get. So this woman's yelling out the window, "Hey, do you believe in the death penalty?" So definitely convenient. She's just going with whoever walks past her. This was our New York, our reporter standing on the corner of New York, just selecting people that walked by. She was doing a convenience sample. Now for her uses of that, it may have been a good method for doing things, but it's definitely not going to be able to be a good, simple, random survey that we can trust the information that we're pulling off of this. The stratified sampling. This subdivides the population into at least 2 different subgroups that share the same characteristics. Then you draw a sample from each subgroup or stratum. So this was, here we're separating the women from the men, and we're selecting 3 out of 4 of each of those. That was when we had the 500 men, 500 women, and then we randomly picked those 500 men and randomly picked the 500 women. That was stratified. That you've already subdivided them into each group. Now, if it was some sort of sampling technique or some sort of response that you absolutely needed to have a good sampling of men and a good sampling of women, or with election type things, they might need to have a good sampling of Republicans, a good sampling of Democrats, and a good sampling of independents. And so they might try to make sure they subdivide those first and then randomly select from each of those different categories. So stratified sampling is definitely something that happens, especially those times when you need something from each different group. But it's not a good, simple, random survey. It could still be a random sample, but it won't be a simple random sample when you've already subdivided and then pick a certain number from each of those different sections. Cluster sampling. This divides the population area into sections or clusters, and then you randomly select some of those clusters and choose all members from the selected clusters. So that was our New York precincts, where we were picking a New York precinct and interviewing everybody that exited out of that polling district, got interviewed to see what was going. And so this time they're doing 2 different polling precincts and doing the same kind of concept. This would be, what do we call it? It's the CSIP survey that we do here at the end of the semester. So at the end of the end of the spring semesters. That NCMC will randomly select a certain number of classes, and everybody in that class is given this SESI survey to be able to see what your college experience has been like for this past year. So it is a cluster sampling where they have now looked at every single class, they pick a bunch of them, and out of those different classes, they give everybody in that class that survey. It's not a simple random survey, but it is a random sample because you do have everybody having equal, everybody, I guess it's not even necessarily completely random because everybody doesn't have an equal chance of being picked. But it does give us a pretty good overall picture of what's going on. But it's not a good simple random survey. So out of these different types of surveys, And hopefully, and as we're doing things, we're going to assume people have found a way to do a simple random survey, or simple random sample, that we're getting a good sampling technique done. And like I said, you'll hear simple random sample over and over and over throughout this semester, because that has to be a first assumption, is that we have brought the data in well before we start trying to calculate anything from it. We have different types of studies that can be done. One of them is a cross-sectional study. This is where data are observed, measured, and collected at one point in time. The United States does a census. They take the age of every single American on April 1st of that year. That's a cross-sectional study. You're taking a moment in time and you're getting information about it. It doesn't have to be a census where it's doing it for everybody. It could be that you're doing it from a sample, but it's still that cross-sectional study is that you're picking a moment in time and using that information. The other option, or another type of study we can do, is a retrospective or case control study, where data are collected from the past by going back in time. So this might be that you're examining records or doing interviews. It might be trying to determine something about cancer and going back in time to see, well, those people, early on, they didn't recognize the link between lung cancer and smoking. And so it could be a retrospective survey that you go back and look to see, were certain individuals that had lung cancer, were they smokers? And those people that didn't have lung cancer, were they smokers? That could be a retrospective survey where you're going back in time and trying to see how much of a connection there was and looking to see if there's still, and how that correlation still exists. A prospective or longitudinal or cohort study. Data are collected in the future from groups sharing common factors, called cohorts. That was that example that we talked about with the nurses, where those nurses were a cohort. They all shared the same characteristics, and just the fact that I think they were all female nurses. And so taking that group, and they followed those into the future. A lot of times you'll see prospective studies done on premature babies. So those babies that were born prematurely, they'll follow them into the future and look at how is their physical development going, how is their emotional development, their mental development. Are they, by the time they get into school, are they at the same level as other kids their age? Or are they behind, and following them into the future and looking at them as they go along and seeing if there's any kind of relationship between things. So they picked a group that has a certain characteristic, and they're following them along as they go. Questions on any of those? All right, some other techniques that we have to think about. Blinding is one technique that's used in which the subject doesn't know whether he or she is receiving a treatment or a placebo. Blinding allows us to determine whether the treatment effect is significantly different from a placebo effect, which occurs when an untreated subject reports improvements in symptoms. If you're talking about a new diet pill coming out, if you're trying to see if this diet pill really is effective, just the fact that somebody knows that they're taking a diet pill might just change the way they think, because now they're saying, all right, this diet pill is supposed to help me lose weight. Maybe I should spend an extra 20 minutes each week exercising. Well, that change in their lifestyle has now changed the fact that they're probably going to lose more weight because now they're exercising more. Or it might be that they know, oh, this new diet pill is supposed to make my hunger a little less, and so I'm going to eat a little less just because I've mentally changed my opinion. So when they're talking about doing these new things, they should obviously be an experiment. They've picked people, and they're looking at that control of giving some the diet pill, giving some people a placebo. They just give them a sugar pill. And just check to see, okay, by taking the sugar pill, have they also lost weight? And if they have lost weight, is it comparable to the weight loss of people that are now on this diet pill? And so that blinding is, you don't know if you're taking a good medicine or a new medicine, or if you're just taking a sugar pill. You don't know which one of those two you're on. So you just have the assumption that you're in this new group. So a lot of times with medications and stuff, they definitely put you into that blinding. I don't remember how many years ago, it's been a long time ago, they had a movie out about instructors that had taken a group of students that were their lowest level students and just went in there with the assumption that they had the best students. And just that assumption that you had good students versus the assumption of having low level students changed what their expectations were, and they really brought them up to, I think they were doing calculus before the end of that year. And so the way that you go in there with your attitude can definitely change what kind of results are expected out of things. And so blinding of not knowing the background of those students can make a difference. Questions on finishing up chapter 1? So definitely with chapter 1, it's a lot of new terminology. This test will have some multiple choice questions on it. And so you'll have to recognize the terminology to match the definition with the different terminology. A lot of those terms will come from chapters 1 and 2. Chapter 3, we actually get to start doing some actual calculations and stuff with things. But these first 2 chapters are really throwing a lot of new terminology at you. Again, terminology that you'll continue to hear throughout statistics. And so you want to make sure you understand some of that. All right, chapter 2 then, kind of previewing where we're going. We're going to look at the important characteristics of data. Some of the important characteristics of data that we need to know. First of all is the center. The center is a representative or average value that indicates where the middle of the data set is located. So trying to describe our data by saying where is the center. And each one of these we will focus in on a little bit more. So I'm just going to kind of quickly go through these to begin with. But if you were talking about this different, we've got east, west, and north for each of these different quarters. And if we're trying to compare where the center is for each one of these different regions, there's different ways to calculate center. It's not always just the mean, which is your average, that middle, adding the numbers up and dividing by how many there are. That's one way to tell me where the center is, but there's other ways to describe the center, and we'll look at those in just a little bit. So center tells me something about that data. The variation tells me stuff about the data. That is a measure of the amount that the data values vary. This describes how the data is spread from the center. When you're looking at a lot of data, is all of it really close together, or is it spread really far out? So how that changes, if we're looking at test scores, and everybody, if the middle test score was an 80%, but everybody's score was between an 78 and an 82, then that's not much variation in test scores. On the other hand, if the middle test score was an 80, and the test scores range from a 20 to a 100%, that's a lot of variation in the test scores. And so just knowing how much they vary tells you a lot of information. And so that's one thing that you want to look at as you look at that data. Also the distribution, which is the nature or shape of the spread of data over the range of values, such as, is it a bell shape? And the bell shape is definitely one thing we'll be talking about, which is called a normal distribution, where kind of looks like that. Your bell-shaped distribution, a lot of things naturally fall into bell-shaped distributions. If it's a bell-shaped distribution where the majority of the values are in the middle, and it just sort of spreads itself evenly in both directions from there, and it just sort of falls off as you get further to the extremes, it's less likely to happen. Having that nice bell-shaped distribution is a good one. A uniform distribution means, are all the values the same? If we had test scores and we had the same number of A's, B's, C's, D's, and F's, well, that would be a nice uniform distribution. More than likely, when we look at especially if we look at test scores, a lot of times you get the skewed distribution. A skewed distribution, especially in our test scores, it's not a very good one yet, and here, might look more like this, where we got a lot of people that are getting the A's and B's, and you get a few people that start falling off. At least this is my hope, maybe I should say, for our distribution, is that we have a lot of people that are up here in the really high scores, and then it levels off to hopefully not much of anything down at the very end. And so this one is skewed. It's not having all the values evenly distributed, and it's not having a good normal distribution. We also have the options, it doesn't say it here, of bimodal, where you might have a bunch of one and a bunch of another. So you might have a bunch of A's and a bunch of F's and nobody in the middle. So that would be another type of distribution that we could be able to look at. So how is that looking? So on this bimodal, we can have a lot of variation. The middle values right here, but there's hardly anybody who has the middle values. They're on both of those ends, which is a lot different than our normal distribution where the middle's here, most people are in the middle values, and then they fall off and hardly anybody's getting A's and F's. So different types of distributions tell you a lot about the data. And graphing our actual data so we can see what kind of distribution we have will be important. Also, are there outliers? Outliers are sample values that lie very far away from the vast majority of other sample values. So if we went back to those test scores that I said we had a lot of variation because we had the person with 20, person with 100%, and so that we had a really big variation. Well, if we go back and look at that data and we see we had one person with a 20, and then that next value was maybe a 75%, and everybody else was 75% to 100, that 20% is an outlier. They are very far away from the normal. And so when you look at those kind of things, a lot of times taking those outliers, and first of all, a lot of times looking to see if they're actually true data, because sometimes those outliers are just because when you're typing it in, it's a mistyping, that you left off a number or transposed numbers or things like that. But making sure it's true values. If it is a true value, we still have to incorporate it in there, but sometimes we keep an eye on that. Maybe it's a true value, but that person was, 5 minutes away from withdrawing from the class, and so that one wouldn't have been a very good, they hadn't been studying for the last 3 weeks type of situation. Also, time is something that we have to look at. Changing characteristics of the data over time. If we were looking at how much money people made, looking at people's salaries. The average salary has been increasing over time. And so to try to compare a salary of somebody in the year 2015 compared to somebody's salary in 1960, you can't say that just because you make $20,000 more, or the same job makes $20,000 more in 2015 than they did in 1960, that they're that much better off. Because the amount of material they can buy in 2015 with that extra $20,000 probably isn't equivalent to the amount of material they could buy in 1960 with that $20,000 less. So trying to make sure that we can keep things comparable as you're doing things. And so that's the reason a lot of times that when you talk about salary type things, that they will compare the buying power in 2015 compared to the buying power in 1960 of similar positions. Trying to keep track of what's going on over time. Each one of these, when you look at data, each one of these will be things that we have to kind of consider what we're doing with them and understanding what's happening. Each one of these are going to be things that we're going to really, almost each one of these will be things that we'll focus on. Look at changing characteristics over time. We'll kind of keep an eye on that one, but it's not as big of a focus as each of these other pieces are as we do things. So each of these, you'll want to recognize those terms as we go through. The book has a mnemonic to kind of help you remember each of those, and that is the computer viruses destroy or terminate, to help you remember the center, variation, distribution, outliers, and time are things that we look at when we look at our data. That each of these have important characteristics that tell us about the information. Because when you're really looking at the data and you have thousands of pieces of information, you don't have time to look at each piece individually. You're trying to look at overall. What kind of conclusions can we come to? And looking at the center, looking at the variation, looking at the distribution, looking at the outliers, and looking at how it's changed over time are things that we'll look for. So that's outlining Chapter 2 in a really quick piece. Starting to look at these a little closer then. If we talk about the frequency distributions. Key concept from this one is when you're working with large data sets, it's often helpful to organize and summarize the data by constructing a table called a frequency distribution. It helps us understand the nature of the distribution of a data set. What page is the frequency distributions on? Or do I even have one on the very next page? Is it 37? Yeah. 47's got one. So on page 47, you can see an example just to kind of give you an idea of where we're heading with things when we talk about these frequency distributions. When you're talking about the pulse rates of females, so the frequency distribution is saying we're putting them in different groups and we're arranging it. Instead of finding out how many people have a pulse rate of 60, how many people have a pulse rate of 61, of 62, of 63, and going with every single number, we say how many of the females had pulse rates between 60 and 69. How many of them had pulse rates between 70 and 79. And so you've grouped the data together, you're summarizing it, and you're looking at what's the frequency of each one of those. So that frequency distribution is also sometimes called a frequency table. Shows how a data set is partitioned among all the categories or classes by listing all of these categories along with the count or frequency of data values in each of these categories. So we talk about them being grouped into these different classes. So then for our pulse rate, it would be first class had pulse rates between 60 and 69. And we looked at the frequency, how often those showed up. Second class goes between 70 and 79. How many of those showed up? Third class is between 80 and 89. What's that frequency? How many of those did we have? So as we look at this, and again, this one has a lot of terminology that we'll be going with. The lower class limits are the smallest numbers of those different classes. So for ours, it was the 60, 70, 80. Those are my lower class limits. The upper class limits are the largest numbers of those different classes. So my upper class limits was the 69, 79, 89. Notice that there is no overlap. It went from 60 to 69, then it jumped from 70 to 79. There's no doubt where each number lands. You don't say it goes from 60 to 70 and then goes from 70 to 80, because then you don't know where do you put 70. You have no overlap when you're talking about these frequency distributions. The class boundaries separate the classes so that there are no gaps. To find the class boundaries, you're going to take half of the original gap and add that number to the upper class limit, and you'll subtract it from the lower class limit. So for our example that we were just looking at, and there is a difference between class limits and class boundaries. Your class limits are looking at the possible numbers that you can have and what is that range for your upper and lower class limits, those possible numbers that can actually fit into there. The class boundaries are numbers that will not actually exist, and then you're figuring out what that middle value is. So for ours, when we did the 60 to 69 and then we did 70 to 79, the class boundary is halfway between 69 and 70. That difference is one beat. Half of that is half a beat. So my class boundary between these would actually be 69.5. Nobody is going to have a heart rate of 69.5 beats per minute. Either your heart beat or your heart didn't beat that minute. They're not counting that it was a part of a beat. And so it's something that cannot physically exist, but you're still saying that that is that middle part, that things are going to fall on one side or the other. So that is your boundary. Your class midpoint. And we will go through and do an example of a frequency distribution next time, and we'll find each of these numbers for those, but I want to go ahead and give you the definitions today. The class midpoint is found by adding the lower and upper limits and dividing by 2. What is that middle value for that class? So for this example where we had it from 60 to 69, you would take the 60 plus the 69 and divide that by 2 to find that the class midpoint was going to be 64.5. The class width, you find the difference between 2 consecutive lower class limits or 2 consecutive lower class boundaries. The class width does not use the upper and the lower boundary or limit for its own class. You take the lower limit of one and the lower limit of the next, or the lower boundary of one and the lower boundary of the next. So for our example, then we would take the lower limit of 60, the lower limit of 70, and we would subtract those, which is going to give us a class width of 10. But if you think about it, it makes sense. There's 10 possible values that can fall between 60 and 69, because you have 60, 61, 62, 63, all the way up to 69 gives you 10 different numbers that can fall in there. So your class width is telling you how many different numbers can fall in it. But it's found using lower class and lower class. And it's going to be the same. It stays consistent through the whole thing. 120 minus 110 still gives me a class width of 10 values that goes in each one. All right, so we will look at an example next time working with these. So we're not going to do any from this section. So I don't even want you to get started on page 52 yet. Just do page 54. Keep in mind, start looking for start remembering to get those blue slips. 3 blue slips means you get to do test corrections on your first test. So those are wise to be able to start going to the ARC, going to the SSS, coming to my office as you work, and working on your homework, and get those blue slips when you work on those so that you can do those test corrections. Our first test is not until, that's the wrong date. Ignore that date. I don't have it with me. It's sometime in, actually maybe the beginning of February. It does.